Thing which I love talking about because I've worked a lot in acoustics. Much of my research was done with flames and acoustics, actually deflagration fronts, compressibility, that's all to do with pressure. And I was working on acoustics and its interaction with burning. Well, obviously I'm not talking about burning, I hope not this time, but I do know what I'm talking about when it comes to acoustics and pressure waves. And it's incredible what's going on. Just to remind you that in the Bible, the Lord is actually, in the last verses in Matthew and Mark, doing amazing things with hearing. And in Proverbs it says, the hearing ear and the seeing eye, the Lord has made even both of them. In Psalm 94 verse 9 it says, he has planted the ear. He that planted the ear, shall he not hear? And it's making a reference to the fact that God has made specifically the hearing. And it speaks of these amazing miracles in Matthew 11. One of them is that the deaf hear. And the famous one with the deaf and dumb man in Mark chapter 7. Ephphatha, be opened, and straightway his ears were opened and the string of his tongue was loosed. Just amazing what the Lord did, instantaneously making people to hear. Well, let's look at the science. What is sound? Well, sound is little pressure waves, very, very small amplitude pressure waves actually going through the air. And that's how we hear. If we took all the air out of this room, apart from the fact that most of you would die, including me, but just putting that to one side, you wouldn't be able to hear either because you need a medium for the sound to go through. Sound has a frequency. How is it measured? Well, it's measured in these units called Hz, which means cycles per second. Low frequency in terms of sound would be somewhere in a rumble of 20 cycles per second. Moving through about the middle of the speech range is about 4,000 cycles per second. And the high speed, the high frequency range is way up in the 20,000. When you're getting old, like when you're in your 20s, you begin actually to, believe it or not, you begin to lose the upper frequencies. When you're getting really old, like in your 30s, it really is evident. And when you're getting to your dotage, which is not far from where I'm going, you know, you really are beginning to struggle to hear all the frequencies. But sound also has an amplitude. How is sound measured in terms of its amplitude? Well, even though I got the wave going transverse, it's really like that, as I said. But it just basically means that you're doing more vibrations. But we measure that in what's called sound pressure levels, which are then converted through a logarithmic scheme, which I'm not going to explain here, but it's converted to decibels. So a millipascal, which is a pascal, is a Newton per meter squared. If you're into units, some of you are, but not all of you are. Don't worry too much about it. But these units are converted to decibels, and normal speech is about 40 to 60 decibels. A jet engine, which if you're at an air display, which I was earlier in the summer, a jet engine at about 100 meters, it's making 128 decibels or thereabouts, which is not far off the threshold of pain at 130. If you're at a rock concert, I'm not particularly advocating it, but if you were, you're often in the region of 120 decibels, and it can be rather dangerous. So you do need to be aware of that. When I was working with wind tunnels in Bedford, when it had wind tunnels, they've all gone now, but Royal Aircraft Establishment, we had to be aware of our ears, and people would lose their hearing if they listened to certain frequencies very loud. The human ear is got an outer ear, a middle ear, and an inner ear. We're going to look at mainly the middle and inner ear, but obviously we mustn't discount the fact that the outer ear is not unimportant. The shape of your ears, and you've usually got two, you might smile, but actually I've met somebody who just had one ear, and we need to be aware that some people could still manage, but it's very advantageous to have two because we're able to pinpoint where the sound comes from with the stereo effect of sound direction. Some animals are actually got that really perfected. Owls have 2 ears, but they're actually at different heights, which is an interesting point, which helps them in actually working out where the sound of a mole or a rat or a mouse is at night. They do an awful lot of their work hunting by hearing. And there is a remarkable shape in our ears, which in recent studies has shown that it's really all part of funneling the sound to go down that little tube. And the little tube is shown here. If I use this here, I don't know whether that's working. Is it? Yes, it is. I'll have to point this on one side. But that ear canal, which is what I'm talking about there, is just the right size, not too big, such that you could actually get your finger down it, and which is not unimportant, because you could damage your ears if you put things in. As people realize, you have to be very careful with that gap. But that gap is very important, as we'll see in a moment, because there is such a thing as resonance. Resonance is when there is something vibrating in sympathy with something else. If the sound is coming in at the natural frequency of, say, a glass, right, it can actually break the glass. Or if the wind is driving over a bridge, as happened in a disaster, I think it was just before the war in America, this bridge actually collapsed. And there was a car on it, and I always want to know what happened to that car, but we won't try and investigate now. Resonance, of course, is very important for when you're actually playing a musical instrument. You set up a standing wave and a flute, depending on the holes that you close and that you open, will determine what sort of standing wave and what sort of frequency you've got. Now that's relevant to the ear canal, which isn't just a hole, as I said. It is actually very important, the shape of that hole, and particularly the length. It's been shown that that tube, the ear canal, is actually just the right length to set up a standing wave which is consistent with 4,000 cycles per second, which, as I said to you earlier, is just the right frequency in the middle of the speech range. So it's actually a quarter of a wavelength, as you can see on this little diagram here. If you're from the engineering side of our group of students here, you can see that you've got you've got an open tube there, and effectively the end of your ear, and that is coming to 0 in terms of vibration, in terms of the amount of openness, as it were. There is going to be a vibration, but effectively you've got a quarter length, and that translates to a frequency of about 4,000 cycles per second. So it's no coincidence that the tube length is about 2 centimeters, which gives you 4,000 cycles per second. By the way, other mammals, of course, do have different ear canals. Not all of them are the same. We're not just talking about human hearing. It's amazing that dogs can hear incredibly well, and they have a very different system in terms of the dimensions of this canal. It actually has a vertical section and then a horizontal section. Cats also have that, but dogs are able to hear up to a much higher frequency than we can, and cats can as well, which is why our cat scarers should work but don't work, because we love birds and we want to get rid of the cats. So we have, these cat scarers, and the frequencies are not something that we can hear, but apparently they can hear. But it doesn't seem to work, because we've even found cats actually sitting on the cat scarers. So anyway, there you go. That's just a useless bit of information. Let's come to the middle ear. The middle ear is frankly amazing, because in the middle ear you've got 3 little bones which we're going to particularly look at. You've got the tympanic membrane, which is the eardrum, right, which is vibrating, and it's actually got attached to it what I will call the hammer. It's got a technical term which I'll give you in a moment. And next to it, it's got what looks like an anvil, so it's actually often called the anvil. And then you've got a third little bone, which looks like the stirrup that you might use to mount a horse or hold your feet on a horse saddle. And we call that the stirrup. The technical term for these three bones is the malleus, the incus, and the stapes. And those bones are tiny, but they're the only bones in the human body, and indeed for all mammals, which don't grow after birth, which is a very interesting point. It's going to be relevant to another issue in a moment. So they stay the same size from when they were formed for a human as a baby, so that you get an idea of size, and you're not used to an American dime on the left there. We've got here a penny, and you can see how small the hammer, the anvil, and the stirrup are. And of course, the evolutionist says that mammalian ossicle bones, which is what these are called, developed from a reptile jaw. So what they tried to say is that the colour of the, if you look on the reptile bottom diagram, they're trying to say that the quadrate bone, which is the dark blue of the upper jaw, moved to become the incus, which is the anvil bone in the mammalian ossicles. Then they're saying that the articular, which is the bottom bone here, because the jaw of reptiles, quite rightly they say, is different to the jaw of mammals. They're saying that that moved and became the malleus, which is the hammer. And then they're saying that the stapes, which for a reptile like a snake, right, it doesn't have these other bones, and they're saying that that stape shortened and became the stirrup that we have in mammalian hearing. Well, that really is just a tale, because frankly all the evidence shows that although there are creatures which do have some very interesting changes to the way they have those bones formed, there is no evidence of movement from a reptile to a mammal in terms of those bones. And if there were, you've got an interesting problem here, because I just said to you that the bones of mammalian ossicles don't grow, whereas the bones of jaws of reptiles do grow. If you look at a crocodile jaw, when it's a little embryo, when it's just been born, come out of the egg, it looks all cuddly, doesn't it? And the little jaw is there. But when you see a full-grown reptile jaw of a crocodile, you certainly don't want to come anywhere near it. It's huge. And this is borne out even by Richard Dawkins, who said the lower jaw, a single bone in mammals, and he's talking in his book, The Greatest Show on Earth, he says, the reptilian lower jaw is more complicated and thereby hangs a fascinating tale that I reluctantly omitted from this book. In an amazing feat, he says this, of evolutionary legerdemain, the smaller bones of the reptilian jaw were co-opted into the mammalian ear, where they constitute an exquisitely delicate bridge to transport sound from the eardrum to the inner ear. Interesting. Let's look up what the word legerdemain means. It means sleight of hand. Synonyms could be artfulness, chicanery, and many other words here. Hocus pocus. I like that. So he is admitting that he's basically appealing to magic craftiness. And indeed, Brian Cox picked this up. Let me play you, I think I've just got time to play you this video, where he is trying to explain the origin of these three little ossicle bones.
Yes, continued. Around 210 million years ago, the first mammals evolved. And unlike our friends the reptiles here, mammals have a jaw that's made of only one bone. A reptile's jaw is made of several bones fused together. So that freed up two bones, which moved and shrank and eventually became the malleus, the incus, and the stapes.
Well, if you have to resort to flick books to make your point, I think that's showing that there is a problem. And this is borne out by the actual literature, which says that the paradox of how the bones of the ancestral jaw joint could function both as a joint hinge for powerful load-bearing mastication, which means eating, right, of a reptile, and as a mandibular middle ear that was delicate enough for hearing, it basically is saying that there is a paradox. How on earth is that creature going to survive, which is supposedly going from one to the other? And of course, there is no answer. Now, it is true that there are some creatures which have a very interesting very, very interesting way of hearing, which is not clearly reptilian or mammalian, but that doesn't mean that reptiles were changing from one to the other. One of them is the duck-billed platypus, but I'm not going to go into that now unless somebody wants to bring it up in questions. So what I'm saying is that those three little bones are absolutely essential to convey the sound of the sound waves and transmit them almost perfectly. It's an almost perfect transmitter acoustically from air, and we're now going to see that you're transmitting the vibrations into a liquid. Now this is incredible. If you do diving and if you're doing underwater swimming, it's very difficult to listen to anything above. You could basically hear nothing because sound bounces off the liquid, whereas this is a clever system for actually compressing liquid, which is essentially incompressible, but it moves, the liquid moves in the inner ear. And we call that inner ear the cochlea, and that's full of fluid. So just to show you what really is happening, so that you get some idea as to the movement of these three little bones, you've got the malleus, the incus, and the stapes. And the stapes is pushing in, or the stirrup we sometimes call it, is pushing in to a cochlea which is full of liquid. In fact, it's got three compartments, which you're going to see in a moment. And the oval window, which is being shown at this moment, is being pushed in by the stirrup, and the stirrup then pushes onto the liquid on the other side, not in the cochlear duct, but in the vestibular duct, right? There's three ducts, and then it goes all the way to the bottom, and then it comes back on what's called the tympanic duct. Now, this is a very old little picture, but it is helpful, because what this shows to you is what's going on is the air vibrating on the left, wiggling these three little bones, which are tiny, and the stirrup is pushing onto the vestibular part of the cochlea, and it's pushing liquid, right, which is because it's essentially incompressible. We've got that with hydraulic lifting systems. Usually we use oil, but you could use water. But most people use oil because obviously it doesn't rust all the machinery. And then you can actually lift 10-ton trucks because you can, essentially the liquid doesn't want to compress. It's actually very, very tiny bit, but it's essentially incompressible. Whereas air, of course, is compressible. So if we unwind the cochlea, what is going on is this is just blows your mind. There's something more to come in a moment, which will even more blow your mind when you become aware of this. You're actually setting up what's called in engineering terms and fluid dynamic terms, you're setting up a standing wave which vibrates at a particular location. Get this. So this liquid is being pushed round, and by the way, because it's a liquid, right, you've got to have somewhere for that to go. So please note, I'm going to come over here this time, that as this one goes in, right, that one comes out. There is a circular window, because it's incompressible liquid, which has got to vibrate 180 degrees out of phase, and if you didn't have that circular window, you would blow the cochlea to bits, right? So you've got to have this second window as well. So you're setting up a standing wave, and depending where that main vibration is will determine what frequency is naturally being picked up by the next part of what we're going to look at. So it's very much location based. If it's a high frequency sound, then everything will happen much more to the left. The standing wave will essentially be setting up a vibration way over here. If it's low frequency, it will be down here. Now, this is interesting because once you grasp that you're actually transmitting something, a vibration in air to a vibration in liquid, you've then got to see where you're going to go next in terms of getting some sort of sense of hearing in the brain. Just to re-emphasize, this is another diagram which shows in fluid dynamic terms that you've got a traveling wave and you're setting up a main vibration just at one location. So we've unwound the cochlea, right, in these diagrams. We've unwound the cochlea so that we can see what's going on. And we are actually setting up a high frequency at one end, such that if the sound is very high frequency, then only the initial part of that cochlea is vibrating. And then if it's low frequency, that it involves an awful lot longer, much longer strip, which is vibrating. So if you find this a little bit hard to understand, and indeed all of us initially, you don't realize the sophistication of what's going on until you really delve down into the detail. I love looking at the detail because it's the detail which shouts design, and yet the detail sometimes is a bit hard to follow. Perhaps a good illustration for this would be an xylophone. If you take an xylophone and you play the notes, you know that the high frequency end produces one note, obviously higher than the other note, other end, which has got wider bars. That's not a completely that's not a complete parallel to the cochlea, but it gives you some idea as to what's going on. It's really to do with the fluid dynamics of what's going on. And indeed, the cochlea is narrower at one point. It's actually narrower at the high frequency end than the low frequency end. So the fluid dynamics of what's going on with the liquid is actually what's driving this, what we call traveling wave, where the major vibration happens at one location. So it's a bit like having a little green man playing an organ inside your cochlea every time a sound is made. And indeed what's happening is that the sound is coming in with many frequencies, and depending which frequency is coming in, not just one part of the cochlea will vibrate, but many parts of the cochlea will vibrate at the same time, because you've got a set of standing waves, not just for one frequency, but a set of standing waves for many frequencies. So you've got layer upon layer of vibrations. But what the cochlea does is split those vibrations into locations effectively on a keyboard. Let me play this little video which may help.
The cochlea now uncoils, and we look at the basal membrane, and now see what happens when we play individual tones. Now a chord, and finally something really complex.
Now, do you get it? So different parts of the cochlea are vibrating according to the frequencies which are coming in on the sound. So as I speak and you listen to me, I'm actually, my voice is carrying many frequencies, and your ear automatically splits the sound that I'm making with my voice into different frequencies with a little green man playing a keyboard. Think of it like that. So let's think of it like that. You've actually got sound coming in. If you're an engineer, you'll understand this. You've got many sine waves coming in, all layered on top of each other, right? If you're not an engineer, think of it in terms of music and the keyboard. And so you've got the cochlea splits the sound up into the many frequencies, which I find stunning. This is an analog frequency analyzer. Your ear immediately understands which frequencies are coming in and says, that one's got to vibrate, that one's got to vibrate, that one's got to vibrate, all at the same time. So let's do a little experiment, which I've already done, of course, with a frequency machine on the computer, digital frequency analyzer. So we'll play a note and see what comes out. There's a keyboard along the bottom of this diagram, and you'll see that the peak is moving, right? Which represents the basilar membrane, which is in the cochlea, vibrating. So, amazingly, the cochlea is so sensitive to frequencies that you can hear not only individual frequencies like that, but you can hear music. And we are hugely over-designed. Because if we were coming from grunts to speech and to sophisticated human beings, nothing in the evolutionary model can explain why you would need this, other than the fact that the Lord has made us with an incredible appreciation of beauty. We can hear this. So I'm playing you a piece of music, and your ear is literally, each little bit is vibrating in exactly the right location, as though a concert pianist was playing John Dunbar's Dance of the Wolves. I find this stunning. We are designed to appreciate beauty, and no evolutionist can explain that. And dogs, okay, they can appreciate music. Stuart, where are you? You're there. Stuart, this is an earlier version of you and Naomi. And this is a dog, right, appreciating music in a way. But it doesn't sing in tune. It would take me another talk to explain why a dog cannot sing in tune. Because we have a connection between our ears and our voice. I do another talk on the voice, and the voice is unique for humans, but that's another talk. So look, just to summarize, you've got this incredible system of sound waves, compression waves coming in through these three ossicle bones, and the engineering is exquisite in the way that it actually converts the vibrations in air to a vibration in a compressible fluid, an incompressible fluid, I beg your pardon, that's the whole point, which needs not only an oval window but a circular window to take account of the fact that you've got to get rid of that compression. And that means that you get frequencies, a whole range of frequencies that you can listen to. But I haven't finished. There is another marvel, let me tell you, of the most amazing marvel, which goes on within the cochlea itself. There is what's called an organ of Corti. Corti, this gentleman who found it, it was quite late on in the 20th century where this was found. I've mentioned the vestibular canal and the tympanic canal. The pressure comes down the vestibular canal, turns around and comes up the tympanic canal when the pressure then is relieved by this circular window. But running parallel with the vestibular canal is the organ of Corti, which is going underneath the basilar membrane, which you can see marked there on the bottom right. Well, what is that organ of Corti doing? Well, it would take a whole talk really to explain the organ of Corti properly. But the organ of Corti has tiny, tiny little hairs, right? And so if the basilar membrane, which is what I was saying was like the xylophone, is vibrating at this location, then it pushes around little hairs, right? You say, why are those hairs important? Well, those hairs are actually what is going to send the signal to the brain. So we've gone from mechanical vibration in air to mechanical vibration in three little bones to mechanical or fluid dynamic vibration of the liquid, which is now going to shake hairs in a particular location. And those hairs are going to send an electric signal. They're going to pick up ions in the liquid, because the liquid, although it may seem that it's like water, it's not water, it's actually a charged fluid. and it's going to send ions, I-O-N-S, down the very hair which is vibrating, and it's going to actually connect with a spiral ganglion nerve which is going to send a signal for that particular frequency to the brain. This is staggering. When I first understood this, I thought, Psalm 139, we are fearfully and wonderfully made. To glorify evolution is frankly, well, there's no other word for it but to say that it's idolatry. This is God's handiwork. He has made these little hairs. Because when I tell you that these hairs they come in pairs, and each little hair is pushed over, and now get this, between one hair and the next, there is literally a mechanical spring. I repeat, when each of these two hairs bends over, there is a mechanical spring which is in that diagram with the green hairs here, which when it bends over, here's the spring, it elongates and it pulls literally a trap door of the hair next to it, and calcium positive charged ions and potassium positively charged ions then are fed down the hair and excite the spiral ganglion nerve, which is connected to every single part of the basilar membrane. Doesn't that make you worship the brilliant engineering mind which has put this together? I think when it comes to the judgment day, the Lord may not say, "Did you not read my word?" He will say, "You studied human anatomy and you did not give me the glory. You studied zoology and you didn't give me the glory. You knew about these things, but you refused to follow where the evidence led. You were not a true scientist." This is a diagram of the hairs, and just to give you the dimensions, a human hair is about 18 microns. These, each one of them, is a quarter of a micron thick. So if you listen to loud music at one particular frequency repeated, snap! The spring is broken. And there's no knowledge yet known to us as to how to regrow those springs, although people are working on it. There's no known way at the moment to mend people who've got broken hairs in the cochlea, or broken springs, I should say. So it is true, is it not, that the hearing ear and the seeing eye, the Lord has made even both of them. I give glory to God. I could talk about the pitch frequency, but I haven't time to do it. I could talk to you about the fact that the spiral ganglion nerves are connected to both sides of the brain. I'll briefly say that the signal is sent from the left part of the brain back to the right hand part of the brain, almost at the speed of light, because the signal is going literally, in electromagnetic terms, it is going at the speed of light, okay? And it's bouncing back and forth between the brain, and if it's speech, it ends up on the left side of the brain. If it's music, it ends up on the right-hand side of the brain. And if it's both, like the voice of my wife telling me that I should have logically done something or not, but I'm listening to her beautiful tones, it's going to both sides of the brain, which is why I get confused. So there you go. The left-hand side of the brain deals with logic, mathematics, science, engineering. The right-hand side of the brain goes essentially to art. That doesn't mean that if you've lost one side of the brain you can't do art, because the brain has a remarkable way, by the way, of sorting itself out when some people are born with only half a brain. But that's another story. Briefly to say that there is also an internal balance system which is nothing to do with hearing, but just as I've talked to you about liquid in the cochlea, right? You've got liquid in 3 semicircular canals. One of them's like that, one of them's like that, and one of them's at right angles again, which means that you can sense 3 movements and stand up straight, okay? And if you want to know whether you've got we were talking about skulls earlier, which were entirely human, that was shown. Homo erectus is human, Australopithecus is not human, okay, which wasn't shown, but Neanderthals are human, okay? Well, we know that they're all human because all you have to do is to look at the inner ear if it's preserved. And if the inner ear, those 3 semicircular canals, are essentially upright, or the semicircular canal is like that, when this skull was standing like that, then you know it must be human. But if that was vertical when it was stooped, then you know it must be ape. There is a clear way of being able to distinguish between skulls, if you've got the inner ear, and often you have, whether they're human or whether they're not. Briefly, let me say this. When people have cochlear implants, you know, they had to be designed. I'm sorry I'm a minute over, but I must just show you this. When people have cochlear implants, they actually thread through an electrode which actually feeds right into the cochlea, and then they excite the electrodes at different locations, and gradually they build up the hearing of somebody who had completely lost their inner ear. In other words, they bypass the 3 little bones. And that was done by a gentleman called Graham Clark from Melbourne, who is still alive. He's a believer. And he had to work hard in order to design the cochlear implant. I would suggest to you that if he had to work hard to design the cochlear implant, that gives the lie to the evolutionist who says that the cochlea, the inner ear, the ossicles, the middle ear, and even the outer ear just came about by evolutionary processes. Thank you.